In 1977, one narrowband radio burst appeared from deep space, lasted only as long as the telescope could watch it, and then vanished forever. A scientist circled the data and wrote one word: wow. Nearly 5 decades later, we still don't have a confirmed source, only competing explanations that fit some clues and fail others. Tonight we rebuild the case from the ground up. What's measured, what's inferred, and why this signal refuses to settle. The signal was detected by Ohio State University's Big Ear radio telescope during a SETI-style sky survey. Big Ear didn't track targets like a typical dish. It relied on Earth's rotation to drift scan the sky. That design matters because it locks the maximum observation time of any sky position into a strict window. The WOW signal was recorded exactly inside that window. The iconic code, 6EQUJ5, is often treated like a message. It wasn't, it was a strength readout, a shorthand way the computer printed how intense the signal was over successive time samples. Jerry Emmon noticed it later while reviewing the logs, circled the line, and wrote, "Wow," in the margin. That human moment is why this single event became legendary. The signal was narrowband and near 1420 MHz, close to the neutral hydrogen line, an astronomically important frequency used widely in radio astronomy. That's why it triggered immediate attention. It looked clean, focused, and astrophysically meaningful. But the same reason makes interpretation tricky. That region is also heavily monitored, and anything unusual demands careful filtering against interference. Big Ear's drift scan geometry allowed it to observe a point on the sky for about 72 seconds as Earth rotated. If a fixed cosmic transmitter sat in that direction, you'd expect a smooth rise, peak, and fall across that exact time window. The recorded intensity pattern did show a rise and fall consistent with something out there, not a random on-off local glitch. But it still doesn't prove intelligence, only consistency with a sky-fixed source. Big Ear used 2 feed horns. A real sky signal drifting through should have been seen again by the second horn shortly after the first, yet the WOW signal did not repeat in the expected way. That single detail fuels a major branch of skepticism. Either the source was transient, highly directional, extremely brief, or something about the detection geometry didn't behave as hoped. The evidence is strong, but not perfectly tidy. The candidate region points toward Sagittarius, but the exact position isn't pinpoint precision. The observational setup creates an uncertainty zone rather than a single star target, which makes follow-up harder. You can't just stare at one coordinate and declare the case closed. This is one reason the signal stayed legendary, instead of becoming a straightforward detection with a mapped origin. Terrestrial interference is always the first suspect in radio astronomy, but several factors made a simple interference story uncomfortable. The signal was narrow, it sat near a heavily studied astronomical band, and the time profile fit a drift scan pass. That doesn't eliminate interference, nothing does, but it raises the bar. Any interference explanation must match timing, bandwidth, and the observation geometry simultaneously. After the detection, Emmon and others attempted follow-up observations and searches. Then later, more sensitive instruments also looked. No confirmed recurrence was found. The lack of repetition is the most damaging piece of evidence for any beacon interpretation, because engineered transmitters generally repeat, even if rarely. And for natural sources, non-recurrence can be normal, if the event was truly one-off. SETI researchers often look for signals that are narrowband, persistent, or repeatable, and sometimes structured or drifting in frequency the way a transmitter on a rotating planet might appear. The WOW signal was narrow and strong, but it wasn't verified again, and its information content is unknown because the recording format was limited. In other words, it looked promising on one axis, weak on another, and incomplete on the third. One widely publicized proposal argued the signal could be hydrogen emission associated with comets passing through the relevant sky region, specifically involving comet candidates like 266P, Christensen. The idea drew attention because hydrogen emissions are near the same frequency band, and comets are real, local, and testable. But the claim has faced substantial skepticism and debate, and it has not become a confirmed explanation. A newer, more cosmic family of explanations suggests the signal could be a brief, naturally occurring flare involving hydrogen, such as a maser-like brightening in an interstellar cloud triggered by a transient energy source. This is attractive because it can produce narrowband features that mimic technosignatures, while remaining purely astrophysical. It's also difficult, because it requires specific conditions and the event would likely be rare, matching the "never seen again" problem. Because we can't go back to 1977, researchers have tried another strategy: search huge archival datasets for similar narrowband events near the hydrogen line. Projects connected to this effort have reported weaker, WOW-like detections in old telescope data, not as proof of the original source, but as evidence that nature can create similar signatures under some circumstances. That shifts the debate from impossible to rare but plausible. Recent reanalyses of the Ohio SETI data aim to refine the signal's characteristics, location bounds, strength estimates, and frequency detail, using improved transcription and modern statistical tools. This kind of work doesn't magically reveal the source, but it can tighten what is physically possible and rule out sloppy explanations. Sometimes mysteries survive because early measurements were coarse. Refining them is how science actually closes cases. The WOW signal is the perfect public mystery: short, dramatic, and forever out of reach. A one-time event is harder than a recurring anomaly because you can't schedule a repeat experiment. That vacuum invites mythology. In science, it becomes competing hypotheses; in pop culture, it becomes aliens. Both are reactions to the same thing: incomplete data with high emotional impact. The serious question is, what physical mechanisms, natural or artificial, can create a strong, narrowband hydrogen-adjacent feature that appears once and then never repeats in decades of searching? That's a constrained problem, not a fantasy. The more we find WOW-like events in other data, the more the balance tips toward rare astrophysical explanations. But as long as the original never repeats, absolute certainty remains out of reach. The next time a WOW appears, we need three things immediately: multiple telescopes confirming it, high-resolution baseband recording, and rapid follow-up across frequencies to check for drift, modulation, and any multi-wavelength counterpart. Modern surveys and automated pipelines are better built for this than 1977 systems. The goal isn't a better story, it's a better dataset. So is the WOW signal solved? Not confirmed, but the best modern work is shrinking the space of possibilities. Contested comet ideas on one side, rare hydrogen line astrophysical flares on the other, and a thin sliver of unknown in between. One signal, 72 seconds, and decades of argument, because the universe gave us a clue without a repeat. Comment the explanation you find most convincing, and subscribe to World of Mysteries for the next investigation.